Okay, so then now I'm going to be back. So in this part, I'm going to talk about. I'm going to talk more about spans in F crystals. First, I want to talk about abstract Hodge polygons. So let me start with this. So abstract Hodge polygons. Hodge polygons. So let's fix a sequence. So fix a sequence of numbers. A0, A1, etc., A2, so on and so forth. Okay, and what we can do is we're going to draw some Hodge polygons using these things. So what we'll do is for each of these lengths, we were going to make draw a function. Let's call it I don't know, f of x. Okay, which is continuous. And over the intervals and let's say here from a0 plus ai minus 1 up to, then we do this. So this is an interval of length I. So this is an interval of length I. It has slope I. Okay, so let me draw one now. Let me give you an example. So this will be the Hodge polygon. So this thing is the Hodge polygon, or the abstract Hodge polygon of the sequence A0, A1, A2, etc. Okay, and so these are non-negative integers. Integers. Okay. So let me give an example. So let's look at this 1, 1, 2. Okay. Usually we want to draw these lines a little bit smaller than the other lines because it starts to grow rapidly. So what it says is now over the first part. So here's the first interval, second interval, 2. Okay. So here we're going to start with slope 0. Slope 0 here. So this is slope 0. So this is the first part. Okay, now over length 1, we're going to go slope 1. Slope 1 up here, like so. So slope 1 this way. And now we're going to go 2 here, and the next ones are going to have slope 2. Okay, so then we need to go, when we go over 1, we go up 2. Okay, so we go 1, 2, like so. And we're going to do it again, up 2. Okay, so like this. Okay, so then so this is, maybe I can squiggle this again. And so this is the Hodge polygon. This is the abstract Hodge polygon. So the abstract Hodge polygon of this number. And so what it does is it'll essentially keep going up and up and up. Okay, so that's what these things look like. Maybe this wasn't the best illustration, but I think you get the idea. I guess one other thing to mention is that here, so this is going to be at point 1. So this is going to be 1 plus 1, and then this one is 1 plus 1 plus 2. Okay, so this is 4, I think, right? 1, 2, 3, 4. Okay, so the endpoints are going to be these points where they break are going to be the sums of these numbers, the partial sums of the sequence. Okay, so this is what an abstract Hodge polygon is, and so let me give you a definition. So the Hodge polygon, or the abstract Hodge polygon of a crystal. So the Hodge polygon of a crystal T will be the abstract Hodge polygon of its Hodge numbers. The abstract Hodge polygon of its abstract Hodge numbers. So the abstract Hodge numbers again, Hodge numbers. Okay, so the abstract Hodge numbers are the slopes that we had. So like here, we did a lot of work to define them, but we again, they're the ranks of these pieces that come with the direct sum decomposition that comes with every crystal. So every crystal has this direct sum decomposition, and so we can define these abstract Hodge numbers. Okay, and so we have this Hodge polygon of this crystal. So now it's kind of like two layers of weirdness, but whatever. So this is what we call the abstract Hodge polygon of a crystal. I now want to define the Newton polygon of a crystal. Okay, so looks like we're doing okay. So the Newton polygon of a crystal. Okay, so what we're going to do is so definition. The Newton polygon of a crystal Okay, so is the crystal, and then we need MF, is the polygon obtained by. Okay, so let me just say this. So what we're going to do is we're going to move over. We're going to essentially join certain vectors end to end, where where the length of these vectors are going to be the number of eigenvalues of multiplicity I. Okay, so we have this thing is polygon obtained by adjoining segments of slope I and let's say length. Well, okay, so length, slope I, let's say over segments of length Ci, where Ci is equal to the number of eigenvalues of f of with the divisibility by p with the p order equal to I. Okay, so this is kind of a weird thing that you do, where you take this thing and you look at its eigenvalues, and what you do is you take all its eigenvalues and you're gonna look at its order, its p order. Okay, so how divisible by p it is, and we're gonna put them into baskets, and we put them into baskets, and we then count how many things are in the baskets, and that's this number. And what we'll do is we're going to make this new polygon, right, where we have each of, so over an interval of however many things are in the basket, we take something of slope I for the ith basket. Okay, so this is kind of a weird thing, but this is going to be a way of encoding the information about the eigenvalues of the Frobenius. It's kind of a fun fact that we don't really need, but that the Newton polygon is completely determines the crystal up to isomorphism. So this is something that's kind of interesting. It determines the slopes and things. Okay. So let me say something else. So let me say another fact about Newton polygons. Fact. The Newton polygon is the same thing. So the Newton polygon of a crystal is the same thing as the convex hull of these collections of I, the order of P of AI, where let's say A0 plus A1T plus dot 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 plus, let's say, A n t to the n is the characteristic polynomial of f. Okay, so what you can do is you can there's kind of two ways of computing this. Okay, the one way is by doing this thing where you look at these eigenvalues of the eigenvalues of this Frobenius thing, or this f for this crystal. First of all, okay, eigenvalues make sense. This is a semi-linear thing. You have to make sense of that. After you make sense of that, you can do this thing where you kind of look at all the things of eigenvalues of order I. Okay. After that's done, okay, that's one way. Sorry, that's one way of doing this eigenvalue way. The other way of doing it is to look at the coefficients of the characteristic polynomial of f, and then look at the orders of this, and then do the convex hull of these things. So you may have some things sitting in the, so you may have like some things maybe sitting inside here, but you'll end up taking the whole of this. Okay. Okay, so the theorems, so the two main theorems, or the theorems that we'll need now that we have all the terminology, is that so it says that the Newton polygon. So okay, so let's take x over k, smooth variety, which is liftable. And what it says is that the Newton polygon will be bigger than the Hodge polygon, the abstract crystalline Hodge polygon, which is bigger than the actual. So then the Hodge polygon from the Hodge numbers, genuine Hodge numbers. Okay, so there's this crystalline Hodge polygon. So this comes from the Hodge polygon of the crystals. So this is the Newton polygon of the crystal, and the crystal that we're considering, we consider in this statement is this dude. So we fix some j, and we do crystalline cohomology of x over k with the Frobenius that acts on here. So so this is the crystal we consider in this statement. Oh my god, that's a bug. Gross. Okay. So so this is the thing that we have. There's kind of two parts. There's this part, and then there's this part. Let me kind of tell you how these things are going to go. So let me just say some things. Okay, so how do we go about doing these things? So we're going to view the Hodge polygon as a function now. So let me tell you a theorem. So let A of x be the Hodge polygon be a Hodge. So this is again an abstract Hodge polygon of some sequence A0, A1, A2, etc. And let B of X be a Hodge polygon of let's say B0, B1, B2, etc. Okay, and so I should say that you can't just so this can be of finite length or infinite length, and truncating or just appending zeros is going to change kind of how this thing behaves. So that's, I just wanted to say that there's kind of a difference between the two things. And it says the following. It says that, so we're going to have this criteria, and it says that this Hodge, so this is kind of a simple, just nothing is really used here at all. It says that one Hodge polygon is going to be above the other if and only if for every n there's going to be a certain ugly inequality. The ugly inequality for A is going to be less than the ugly inequality for B. Okay, so we're going to have two ugly things. Let me explain what ugly this thing is. So this ugly of, let's say for some C, so let's keep it neutral. So I'm going to have some other sequence of C's. So this is just going to be the sum from I is equal to 0 up to m of m minus I of Ci's, like so. Okay? So sometimes you see these sequence of inequalities that look ugly, and this is kind of the criteria that we're going to use for determining when one Hodge polygon is going to be above another. All right. So I want to talk about a way we can think about this and how we can think about this inequality, these inequalities here. So let me get them out again. So we wrote down this system of inequalities here. So we have the system of inequalities, and so when we write them out, they actually become so we have like A0 is less than or equal to B0, and then we have 2A0 plus A1 is less than or equal to B0, 2B0 plus B1, and then we have 3A0 plus 2A1 plus A2 is less than or equal to 3B0 plus 2B1 plus B2, and so on and so forth. And so they kind of go backwards here. And so with these inequalities, again, they keep going. And when we have this one less than this one, so this is going to tell us that this polygon here is going to be below the polygon for A's. So the polygon for B's are going to be below the polygons for A's. So let me write this out. So let me just kind of draw a picture here. So what's going on is that so we're going to have B's. Okay, so maybe we have 3 breakpoints here. Okay, and so this is the point B0. This is B0 plus B1. And then maybe out here this is B0 plus B1 plus B2. Okay, so this has length B0. This is length B0. This is length B1, and this thing has length B2. And what's happening here is that we start out with something, and it starts out with a really slow slope, and then as we go to the next time, we're gonna get an increased slope, and then eventually we're gonna have a very steep slope. So this is the idea of what's going on in the Hodge polygon, and these inequalities, for example, tell us if A0 is less than B0, then it's going to start going up a little bit faster. So here's A0. Here, and it's going to happen before B0, so this is the length here of A0. So it's going to coincide here, and now it's going to start going up less. So maybe A1's going to be down here. So we have this other inequality. So it's going to go along this slope until here, and then this one, it's going to start going its slope even faster. So what this is showing is that this a of x is going to be above b of x. So when you have the inequalities like so, here, the a's are going to be appearing sooner, which is going to make the slopes go up. Okay, that's the idea. Okay, so then that's how to think about these things. There's kind of the babymost case is this one. So this is the babymost. The babymost you can already see. The babymost case is when a0 and b0 are there. Here's another case to think about. So you can actually write out what these functions are, and writing out what these functions are is actually kind of a useful thing. So we can write out what the functions are. So write out what, let's say, a of x looks like. And what a of x is going to look like is it's going to be, well, okay, so we need to find the x. So we need to find the x, sorry, the j, so again, we have this partition. Okay, so we have a0, a0 plus a1, and then a0 plus a1 plus a2, and it goes on and so on and so forth. And what we need to do is we need to find the thing where the interval where x is. Okay, and x is going to lie in between. It's going to turn out that x is going to be in between some partition of these. So it's going to be in between a0 plus a1 plus and aj minus 1, and the next one is going to be a0 plus a1 plus all the way up to aj. Okay, and because it's here, this one is going to be, this is where the slope j minus 1 ends and the slope j begins. So this is going to tell us that, this is going to be a1 plus 2a2 plus plus j minus 1, aj minus 1. Excuse me one second. Okay, so plus aj minus 1 here, plus, and then we have something of slope j, and now we need to take x minus, and then we have the sum, this endpoint, a0 plus a1 all the way up to aj minus 1, like so. Okay, so this is actually what the function looks like for x once we figure out where x lands. Okay, and we can write this out. So that being said, let's write out what it looks like for two things, and kind of show you how this system of inequalities here can be found by looking at the inequalities for a and b, and then you'll get the general idea. So okay, so let's take x to be, let's suppose that we just have two things, a0, a1, and a2. Okay, and then we have b0, b1, and b2. Okay, and then we take x to be above b2, or above the sum of all of these things. So then here we'll have a of x looks like, well, a0, so we have a1 plus 2a2 plus, and then we have, so I slightly messed up my indexing convention, and I'm going to, so I'm gonna write out what b of x looks like. So b of x looks like, so here we have the constant part, b0 plus 2b1, plus, then we have it ends here, so then we're going to have 3 of x minus b0 plus b1 here, like so. So this is what the expression looks like. And then if we actually write this out, these are going to subtract, and what do we get? So we have minus 2b0, so we're going to have like 3x minus 2b0 minus b1. Okay, and similarly we can write out a of x looks like this. So this is equal to 3 of x minus 2a0 minus a1. And if we had that a of x was less than or equal to b of x, what would this tell us? This would tell us that, well, 3 of x minus 2a0 minus a1 is less than or equal to 3x minus 2b0 minus b1. These cancel here. which tells us that B0, 2B0 plus B1 is going to be less than or equal to 2A0 plus A1. And this is kind of where these inequalities come from. That's all I wanted to explain with this example.